Hello everyone. Thank you for joining me at Forest Product Society Virtual International Conference. My name is Adam Wade, a PhD student at Mississippi State University, Department of Sustainable Bioproducts. Today, I will be presenting the study, Computer Vision Wood Identification of North American Diffuse Porous Hardwoods. The co-authors of this study is Prabhu Ravindran, University of Wisconsin-Madison, Alex Wiedenhoff, Center of Wood Anatomy Research, USDA Forest Products Laboratory, Ruben Smolsky, Mississippi State University, Robert J. Ross, USDA Forest Products Laboratory, Frank Owens, Mississippi State University, and Adam Wade, Mississippi State University. I would like to thank and acknowledge the Department of State, Forest Stewardship Council, the University of Wisconsin-Madison, and the USDA Agricultural Research Service for the funding of this project. I would like to begin by highlighting some background information for this project. The United States hardwood economic output was a little over $300 billion in 2016. This economic output includes the initial cost of goods plus the final sale of these goods. The gross domestic product in 2016 was $156 billion, and this includes the final sale of the goods only. The export was right at $40 billion. These markets include sawmills, rail ties, hardwood veneer and plywood, flooring, containers and pallets, furniture, as well as cabinets, just to name a few. When identifying North American woods, one of the first features that we look for is the pore size and distribution of these pores. Broadly, we have two, diffuse porous and ring porous. Diffuse porous woods have low spatial heterogeneity. This is seen with the even pore size and distribution among the early wood and the late wood. Ring porous woods have a greater spatial heterogeneity. This is seen by the larger pores in the early wood and the smaller pore size in the late wood. To help better understand the spatial heterogeneity issue, I have two images here. On the left, we have Quercus nigra, a ring porous species. And as you can see, there's quite a difference between the pore size and pore distribution between the early wood and the late wood. The early wood pores are quite large, and the late wood pores are quite small. Dependent on the specimen, we may not have all of the features needed for proper identification. This is especially true when dealing with fast growth and slow growth specimens, where fast growth specimens can have a larger area in the late wood, and slow growth specimens can have a smaller area in the late wood. The image on the right is Betula nigra, a diffuse porous species, and as you can see, the pore size and pore distribution is relatively the same and even across, even between the early wood and the late wood. And this is typically the same for slow growth and fast growth. Because of this varying spatial heterogeneity and the influence it may have with wood species identification, we chose to separate diffuse porous and ring porous specimens. We will focus on diffuse porous in this study and address ring porous in a future study. As mentioned before, this study we are focusing on diffuse porous species. We took important North American diffuse porous species and divided them into 22 classes, each containing anatomically indistinguishable taxa. The Acer genus was divided into hard maple class and a soft maple class. This separation of hard maple and soft maple is very common for furniture makers and woodworkers, where hard maple is commonly used for flooring and soft maple is not. An important and anatomical feature for distinguishing hard maple and soft maple are the rays. Hard maple has two distinct size rays, while soft maple have more uniform size rays. Common hard maple species are Acer saccharum, sugar maple, and Acer nigrum, black maple. Common soft maple species are Acer negundo, box elder, Acer rubrum, red maple, and Acer saccharinum, silver maple. The fruitwood class contains genera Crataegus, hawthorn species, Malus, apple species, Prunus, which is plums, cherries, peaches, and nectarines, Pyrus, pear species, Sorbus, which is rowan or service tree. The majority of these species feature very small pores that are arranged almost exclusively solitary. Other important classes were the Alnus, which is very common for guitars and also very common to have the large aggregate rays. We have Betula, that is very common for plywood, liquid ambar, that is common in furniture making, and Tilia, which is common for wood carving due to its low density. It is also important to note that we have a Prunus class that contains solely Prunus serotina. Currently, wood identification is performed by human observation of anatomical features using a hand lens and/or a microscope. Once these features are observed, they are then compared to reference descriptions, identification keys, or even verified specimens. As reported on Wiedenhoff et al. 2019, there is a severe shortage of wood anatomists that can ID wood at a forensic level. It is difficult to train and sustain this expertise, which requires several months to years to become proficient. There is a need for automated solution, and computer vision identification has potential to be the solution. In this study, we specifically used the XyloTron platform. The XyloTron is a computer vision-based system designed at USDA Forest Products Laboratory. It is open source and all of the components can be bought off the shelf. You can go home and build one as the designs are available online for download. The components of the XyloTron are the camera, the XyloScope, and the laptop. We also have software that uses convolutional neural network for identification. The model is trained by preparing the specimen's transverse surface so that all the features are visible and free of artifacts. Many images are then captured, and then the class membership of each image are designated. The model is then trained and the performance is evaluated, and this is repeated as needed to finalize a metrics-driven deployment model. Operation of the XyloTron is fairly simple and straightforward. First, you take the prepared specimen on the transverse surface and then place the XyloScope flush on the specimen. You capture an image, wait a few moments, and then an output is given to you with a confidence of 0 to 100% for each class. Our objectives of this study was to develop a CNN model on the XyloTron platform to identify important North American diffuse porous species. Evaluation of the model at a specimen level, and to ready the model for on-the-ground deployment and evaluation. Our ultimate goal is to have a fully operational North American model ready for deployment. As mentioned before, we are starting with the diffuse porous woods, where we are simulating real-world field testing using independent xylaria between the training and the testing data. And this brings us to our materials and methods. Here, I would like to highlight the different xylaria that we used for the training and test models. 3 xylaria were used for the training model, and 1 independent xylarium was used for the test model. This approach of testing models on specimens from a xylarium that did not contribute data to model training was employed as a logistically manageable, practically useful surrogate for real-world field testing. The ultimate test of any automated wood identification system is in-country field testing, but the main challenge is the requirement of a wood identification expert for the validation of the specimens that are being tested. Using the XyloTron, we collected 6,393 images across 788 different specimens. The high-level process of sample preparation for these 788 specimens was done by polishing the transverse surface using a rotary disc sander. We used progressively finer abrasive discs from 220 to 1,500 grit sanding discs. Removal of dust was performed between each sanding disc using compressed air and adhesive tape. The image collection was performed by using the XyloScope to take multiple non-overlapping images per specimen on their transverse surface. The dimensions were 6.35 mm by 6.35 mm, 3-channel RGB images, and had pixels of 2048 by 2048. There were Linux-based and Windows-based versions of the XyloTron software used, along with multiple XyloTrons and multiple operators with varying skill levels and experience. Here we have the model architecture and training. We augmented a ResNet 34 backbone with some custom layers, trained the model with standard tricks using two-stage transfer learning. At the end, we get a trained model that predicts the class of an input image. This was mentioned in more detail in the computer vision identification of Peruvian woods presentation by Dr. Frank Owens. This brings us to our results. Here we have the model evaluation. Shown is a confusion matrix for the five-fold cross-validation model on a specimen basis. As you can see, we had a 95.2% accuracy, and only 24 of the 504 specimens were misclassified. Each of the 504 specimens contributed images to exactly one fold. For a correct evaluation of a trained model's generalization capability to unseen samples, this specimen-aware partitioning of the data into folds with distinct specimens is required. It should also be noted that cross-validation analysis did not include specimens from the PACW xylarium. Here we have the model evaluation summary. We have the five-fold cross-validation training model, the field models, PACW top 1 and PACW top 2 accuracies. We did standard five-fold cross-validation, then we take the entire training data set and train one single model, which we call the field model, which is evaluated on the PACW specimens. The cross-validations are trained with 80% of the data, while the field model is trained with 100% of the data. Predictions of the trained models were evaluated at the specimen level, with the predicted class for a specimen taken to be the majority of class predictions for the images contributed by the specimen. Accuracies based on the top prediction for each specimen are reported for all the models. Additionally, the top two image level predictions are aggregated with equal weights to generate the top two predictions for a specimen. If the true label is one of the top two specimen level predictions, the specimen is considered to be correctly identified. It is also important to note there is a loss in accuracy during deployment as seen in previous studies. Ravindran et al. 2019. Here we have some examples of misclassification. On the top, we have anatomically consistent taxa, and then the test specimen being typical. The images shown on the left is the Acer sacrum. This is in the Acer hard class. Acer saccharinum, which is in the Acer soft class. This is consistent with wood anatomy and the kind of misidentifications likely to be made by human field inspectors, where the main difference in identifying of these two is the rays, where the hard maple will have two distinct sized rays and the soft maple will have uniform sized rays. On the bottom, we have another type of misclassification. This misclassification is inconsistent with macroscopic wood anatomy and would not be expected to be made by a human inspector. Here we see Betula nigra, which is in the Betula class, and Crataegus mollis, which is in the fruitwood class. And as you can see, the pores are greatly different in size as well as some arrangement. To highlight a few of the takeaways from this presentation, we talked about a development of a national scale model for North American hardwoods. And due to the varying spatial heterogeneity between diffuse porous and ring porous woods, this study focuses on the diffuse porous woods. We also talked a little about the specimen level evaluation, as well as generalization demonstrated by running a model on test specimens from a separate xylarium. This model appears to be robust to different operators of different skill levels, as well as using different XyloTrons. This proves to be a useful surrogate for real-world field testing. Moving forward, we would take the PACW specimens and then fold them into a new field model. We will also conduct real-world field testing along with independent validation of these specimens. Then we will deploy this model for actual real-world use. I would like to thank everyone for joining me and thank you for your attention today. Now I'd like to open up for any questionings.